All right, thank you very much. I want to talk to you today about the wide range of libraries and frameworks and just the concept of CUDA-X. Jensen talked about in the keynote, that we built CUDA over 20 years ago, and CUDA is this core foundational software piece that marries our hardware to your software. And CUDA-X was the next logical step for us, that if we want to accelerate every possible workload, that we need to build libraries and frameworks to enable you to do that. And so not just accelerating a single application, but developing libraries that will accelerate all applications. And really, we've applied it in so many different domains. You can see here, computer-aided engineering, computational lithography, quantum computing, genomics, and so many more. And we build these things because I heard Jensen say yesterday, we're really nothing without our developers. We need to be able to reach every possible developer in every domain. And so we can't build everything, but we can enable you to build these things. And so I do want to start with what we kind of consider our love letter to our developers.
To the creators, the pioneers, the builders of the future, CUDA was made for you. Since 2006, 6 million developers in over 200 countries have used CUDA and transformed computing. With over 900 CUDA-X libraries and AI models, you're accelerating science, reshaping industries, and giving machines the power to see, learn, and reason. Now, NVIDIA Blackwell is 50,000 times faster than the first CUDA GPU. These orders of magnitude gains in speed and scale are closing the gap between simulation and real-time digital twins. For you, this is still just the beginning. We can't wait to see what you do next.
So in the end, all of the technologies we build and all of the libraries, all of the frameworks, all of the models we put out there specifically because we know that we can't have every idea, we can't build everything, but we can enable every developer. And so I'm going to dig into a few key domains. I don't have time to go through all 900 of our models and libraries and frameworks, but I can pick out several that are related to the domains of science and engineering. And the first one I'm going to dig into is what we call industrial engineering, which is computer-aided engineering and electronic design automation. So computational lithography, things like computer-aided engineering, and AI physics. And we'll dig into a few of these libraries. It's really important to us that, especially in these domains like CAE, that we come to market through our partners. Again, I heard Jensen say last night, you can't come to us and buy these things. You go to our partners and buy them. And so you can see across the bottom, every major ISV is partnering with us because they understand the value that our platform brings, whether it's through the hardware and also the software that enables it. And across all these things, computational lithography, compared to the state-of-the-art on a modern CPU, we can get a 20x performance speed up using cuLitho. CFD is really an important space in a variety of different domains. And in CFD, what we've done is we can both accelerate the CFD solvers directly through libraries like cuDSS, the direct sparse solvers, which I'll talk about on the next slide, but also through AI physics models. So we can accelerate the solvers themselves, the applications, to get you high fidelity results, but then we can take those results and we can feed them into AI surrogate models to accelerate the design process. So across each of these, each of these domains, we've picked out a representative workload, a representative application, and compared against the state of the art on a modern CPU versus running GPU accelerated using many of these partners here. And an important library that we've developed and released fairly recently is CUDA-X. So sparse matrices are an important part of many science and engineering domains where the matrix itself is very large but filled primarily with zeros. And you have to, if you were to calculate this full matrix, it's hard to fit it in memory. You're limited in memory space. You're also limited in compute because there's no point in calculating all of these zeros. So there's a variety of techniques to try to optimize sparse solvers, and one of those techniques is using CUDA-X. This can be used in nearly every domain. So up top here, looking at in automotive, doing things like fluid dynamics or structural analysis, aerospace, very similarly, airflow simulations, electromagnetics, and also in the semiconductor space for circuit simulation and so on. And so in each of these parts, so when you're doing a sparse matrix solve, there's the factorization step, there's the solve step, and then the reordering to get it back into the matrix. And in each of those steps, you can see a speed up from CUDA-X. So talking to our customers, obviously these are fairly extreme cases here, showing the 80x here. But many of our customers, when you run full applications, not just doing the individual solves, report 5 to 25x faster on average compared to, again, their CPU solvers. And here are some of the key software vendors that have already adopted CUDA-X, which at this point hasn't even reached 1.0. It's still a fairly young product, and we're already seeing strong adoption and strong speed up from them. And we're also working with a variety of partners to make sure that when they're doing their scientific simulations, that they're doing it on our platform. So on the top left there, you can see an example with BMW in a virtual wind tunnel. That virtual wind tunnel actually is available online for free. It's a reference workflow to demonstrate to you how you can combine various technologies like Omniverse and Physics Nemo to build an engineering workflow. Earlier this year, we had a demonstration with Boom Supersonic and Rescale. This airplane is a supersonic passenger airplane, and in order to be certified to fly over land, over populated space, they need to reduce the sound of the sonic boom, and so they've designed this aircraft. So we demonstrated at GTC in San Jose where you can vary the Mach number and see the results of that sonic boom. You see, working with a variety of other vendors here. I would encourage you to actually come by the booth if you haven't already. We have a demonstration, something very similar to that top left there, using a commercial airliner, and we're showing how you can, as an engineer, vary the geometry of the wing, vary the angle of the airplane, and in real time see the effect of that. And we trained that using almost 2,000 different real simulations using a solver from one of our partners, and then built a surrogate model so we can make it interactive in real time, which enables engineers to then explore a much wider range of possibilities before then choosing the subset they want to simulate in high fidelity or even in physical modeling. So all of that, the surrogate models come through a package called Physics Nemo. Physics Nemo is an open source software product that we have out there, and it has a variety of different AI physics models built for you. So you don't need to read the literature and build for yourself using something like PyTorch or TensorFlow. We've built these models for you, and you can then bring your own data and train it up using your data. But we've also released now pre-initialized solvers. So it's we've started out for you with a starting point. So here, based on automotive, a basic model with automotive data, and then you can fine-tune it yourself. So you might imagine that perhaps GMC, who builds all trucks, versus Ferrari, who builds very fast sports cars, they may want to fine-tune differently based on their own commercial interests, their own data. So they can start off with a pre-trained model and then fine-tune it to their own geometries and needs. So this is Domino is the name of the neural operator network based in Physics Nemo, and then these are the pre-trained versions there. You can see you can get a fairly significant speed up over standard accelerated CFD solvers. And this enables the workflow to happen much faster. So by using the simulation, that feeds into these solvers, which enables engineers to iterate faster, iterate on more designs, interact in real time with their designs, and build better products more quickly. And so this data comes from a study that we cite here below, where back when automotive design relied on physical wind tunnels, they would build a clay model, they'd build a model of their car, they'd put it in a physical wind tunnel, and they could test maybe one per week, because they had to build this model out of clay, put it in there, study it. Through simulation, they were able to get it to about 1 per day. Using accelerated solvers, they could get about 300 per day, and then according to one of our partners, that now using these AI physics surrogate models, that they can evaluate 10,000, they've actually said over 17,000 different models, and really tweak and understand the effect of their changes. And I referenced this just a moment ago. We have this blueprint for real-time CAE digital twins. This is up on GitHub. If you would like to build your own model based on physical AI physics and Omniverse, we've created this reference workflow where we've created this we call a NIM, NVIDIA Inferencing Microservice for CFD. We've plugged that in with Omniverse and built a wind tunnel for you. This is not meant to be a product. This is not necessarily something that you would use in production, but it demonstrates to you if you want to replace the visualization engine. You have the starting point for the rest of the pipeline. If you want to train the network yourself instead of using the network that we've provided, you can do that. And so this is a reference for you to build your own workflows. And we've seen a variety of customers and partners take that workflow and do some really nice things. That's engineering, CAE, and EDA. What about climate and weather? And I do want to take a second to differentiate between the two of those. So weather is what we're used to. You're looking forward the next couple of days, next couple of hours, next couple of days of what to expect. Climate, then you're looking over years, decades, and centuries. So same foundational math is being done in those cases, but you have to make certain trade-offs. If you're simulating over the course of a century and you want to do it in a reasonable amount of time, you need to trade off your resolution and things like that. For weather, similarly, if you make it too high resolution, then by the time you know the solution and can predict what the weather's going to be, it's already happened. So you have to make these balances and trade-offs. Earth-2 is an initiative to create a digital twin of the Earth, and can be used both in climate and weather. And so here's one more video for you about how we're using Earth-2.
On Monday, the storm will veer north again and approach Taiwan. There are big uncertainties regarding its path. Different paths will have different levels of impact on Taiwan.
Imagine a world where we can predict the future. Digital twins are virtual models that mirror the real world and let us see the future to better understand the impact of today's actions on tomorrow's world. Meet NVIDIA Earth-2, a digital twin that uses the power of AI, physical simulations, and computer graphics to make weather and climate predictions at a global scale. CoreDiff is NVIDIA's generative AI model that was trained on WRF numerical simulations to generate weather patterns at 12 times higher resolution, from 25 kilometers to 2 kilometers. This is a monumental leap in regional weather prediction, and remarkably, Core Diff AI does this 1,000 times faster and 3,000 times more energy efficiently than traditional physical simulation methods. Here in Taiwan, the Central Weather Administration is using these models to forecast typhoon landfalls with more precision. But we are not stopping there. The next frontier is hyperlocal forecasting down to tens of meters, where the effects of city infrastructure are taken into account. Core Diff AI is also being trained using high-resolution data, such as that generated by Palm, a physics model that simulates atmospheric and oceanic boundary layers. When combined with weather simulation wind fields, it can model the airflow around buildings. We expect to predict phenomena such as downwash, where strong winds funnel down to street level, causing damage and affecting pedestrians. NVIDIA Earth 2, an excellent example of a digital twin that fuses AI, physics simulations, and observed data, can help countries and companies see the future and respond to the impact of extreme weather.
So how is this applicable to everyday life? Well, there's you saw in that picture of the storm, you may have noticed there was lots of little paths that were shown. So when you're predicting a storm, frequently each model, or even the same model run multiple times, will predict a slightly different path. And if you're limited in how many times you can run and how many predictions you can make, then you can only predict the common path and hope for the best. What we have actually seen is by accelerating this, by doing more predictions, yes, you can increase confidence in what the likely path, but you can also detect less likely paths. And there was an example a couple years ago of a storm that took one of those unlikely paths. And we were able to, within this model, be able to predict that path that was not discovered by more traditional models. You're also able to take, I mentioned the trade-offs between resolution and being able to get your results in a reasonable time. You could take the low resolution and produce what's called downscaling, which is actually sounds a lot like upscaling a movie, right? If you have an HD movie and you want it on a 4K movie, you would upscale it. In the domain of weather, you would actually call it downscaling because you're going to a finer grid. But you can take these coarse results, and project them to a finer grain. And that means that if you're making a storm prediction, instead of maybe predicting at a zip code level, you might be able to predict at a neighborhood level and be able to provide advance warning of these storms. That's really useful for things like, I know the US military uses weather prediction before launching their planes and putting them in the air to understand what sort of weather to expect along a mission route. You can understand that insurance companies would want to be able to predict the sort of weather or the effects of climate change in individual areas. So there's so many ways that this is applicable to our daily life. And Earth 2 really fits all of those use cases, from downscaling using things like Core Diff to creating a virtual model here. And in this picture here, if you go down to our booth, it's actually in the corner of the booth, you can pick a day of the year and a particular lat and longitude, and it will allow you to create a storm at that location and then model what it would do if that storm were to start on that day in that location. So it's really great for prediction. And again, insurance companies and other commercial airlines, any of those can benefit from those sorts of predictions. So I encourage you to go check this out in the booth. Data science, actually the previous talk talked a little bit about some of our data science libraries. So here we'll talk a little bit about cuOpt and CUDA-X. If you're doing data science, you're probably using something known as a data frame, either through a library like Pandas or Polars. CUDA-X is a way of taking that data frame and moving it to the GPU, and so when you're slicing your data, all of that's happening on the GPU. So in terms of data science, these represent a variety of different ways that you can perform data science. So things like The data pre-processing, I believe that's using CUDA-X here. You can see roughly a 50x performance improvement doing that on the GPU versus leaving it on your CPU. Route optimization. Jensen, in his keynote earlier this week, talked about cuOpt and how it's breaking records over and over again for optimization problems, things like the traveling salesperson, any sort of optimization problem. And in fact, if you begin to look for it, if you know the pattern to look for, optimization problems are all over the place, and that's why cuOpt has become a really important library. And again, this is one that is less than a year old, and it's already making enormous impacts. Whether you're looking at the best ways to allocate your resources, optimize for risk or for inventory control, supply chains, pricing. The finance industry loves optimization problems. Any sort of prediction. These optimization problems are running fastest with cuOpt, and that's why you're seeing adoption from so many different partners here. And really, if we look at data science in general, taking a step back from cuOpt and just look broadly at things like rapids, at things like CuPy numeric that was mentioned earlier, JAX, all of these are using CUDA-X under the hood. And so these are all enabled through our libraries. cuDNN is, Jensen described as kind of the original CUDA-X library, that it enables so many of these products to reach the GPUs. And then cuDNN is just one of many of our libraries that sit underneath all of these providers and all of these libraries. So if you're doing data science, you're almost certainly doing it on NVIDIA GPUs. Moving on to computational biology. In many cases, these are higher level frameworks that are being done. Things like Parabricks and BioNeMo. BioNeMo is a class of AI models being used in biology. Q-equivariance and Q-tensor, however, are much lower level libraries that are being used in things like quantum chemistry. So life science, what's interesting compared to other domains that I'm more familiar with, I've worked in, that I've done more work in, is really built around workflows and breaking the work into a pipeline of tasks. And so taking just this picture from an electron microscope and processing it, you need to be able to read it in, to digitize it, to analyze it using things like rapids for data science. BioNeMo is a model that enables you to do various transformations. Q-equivariance is an interesting new addition to CUDA-X, where you need to be able to, actually, let me move to the next slide to be able to show this one. If you look here at this molecule, if you wanted to do drug discovery, for instance, and find particles that will bind up with these molecules, you need to be able to rotate it in every different direction. So equivariance here, what that allows you to do is be able to do these transformations, and the work remains, the geometry essentially remains the same. So equivariant neural networks, if you make a change, it has a predictable outcome, essentially. And so these use cases where it's being used in things like AlphaFold, and things like, and products like Allegro, and for protein folding for docking, which is finding these particles that will bind up and potentially look towards being made into medication and drugs and so forth. Generating crystals for superconductors, things like that. All of these require that property of being able to transform and get predictable results. So Q-equivariance is having an enormous impact in computational biology and those and related fields. And you can see, again, many of the partners that have adopted that. Life science in general, it's one of the earliest domains that saw speed up from GPUs. And you can see here many of these different operations people are doing for medical imaging, where you can ingest the images and act on them, to sequence alignment and genomics. All of these workloads speed up on NVIDIA GPUs. And lastly, I want to talk about quantum computing. Here we'll talk about cuQuantum, which is the library that's used to accelerate every major quantum simulator, and CUDA-Q, which is our programming model and platform for quantum. So it's when we work with every major QPU builder, so you can write something with CUDA-Q and be able to run it no matter what type of QPU you're running on. And actually down in the booth, you'll see 3 different modalities represented there, and CUDA-Q will run on all of them in addition to simulation. So a few years ago, I think it was 2023, 2 years ago, Google demonstrated the first logical qubit. And if you watch the keynote, Jensen explained this, that qubits themselves are not very reliable. They're a bit unpredictable. And the logical qubit binds them together to make them more reliable and easier to use. But that was just one logical qubit. In order for a QPU, a quantum machine, to be truly useful, you need dozens or even hundreds of these logical qubits. So we're seeing this progression from our partners. Each of these dots represents one of the major quantum computing vendors. We've just left off exactly who they are or which modality, because we don't want to pick favorites. And you can see this progression through time, that more and more of these logical qubits are getting stitched together. So this is really an important era to make quantum computing more useful. And we believe that NVIDIA provides a lot of value in quantum computing both today and into the future, which is reflected in this video. And I don't think there's any sound on this one, so I can talk through it a little bit. But here you can see our vision is that the QPU will sit right next to an accelerated supercomputer. And NVQLink was announced this week as a natural connection between our AI supercomputer and our quantum processor. And we're representing here the 3 major modalities of quantum computing, and we're able to connect to each of them. We truly believe that it's not a quantum or classical computing, it's quantum and classical computing, so it's always going to be useful to have this AI supercomputer next to it. It's going to be useful for things like quantum error correction, to be able to make these logical qubits and make these machines useful, but also because applications, we think, will continue to be hybrid, that you'll have classical operations that feed into the quantum, and then quantum will feed back. And so just like the GPU for many years was the processor that sat alongside the CPU to accelerate certain applications, we believe the QPU is going to sit right alongside a classical accelerated supercomputer, and then they're going to work together. And CUDA-Q was built as a platform to support that, to support hybrid applications that run both on the accelerated supercomputer as well as the QPU. We really took our expertise building 20 years of platform for GPUs, and we want to apply that so that as QPUs become more useful and as they come to market in the future, that you have a platform that's stable and you already have algorithms being developed and developers and users are ready to go. So we fit in a variety of different places. So from the first few logical qubits, which is where we are today, to this future where there's thousands of logical qubits, and here you can see many AI supercomputers linked together with their own QPUs. To get along there, what do we need? Well, we need to develop algorithms. Well, today you can develop algorithms in simulation on NVIDIA GPUs using cuQuantum under the hood. You need to be able to design these processors that are going to run those qubits. Well, you can do electronic design automation. You can do the equivalent to computational lithography for qubits to build better QPUs. You need to be able to generate data. That data is going to feed into quantum-inspired neural networks. You need to be able to build hybrid applications. And again, today you can begin to build those where parts are running on the GPU and parts are running on the QPU, whether it's simulation or an actual physical QPU. And eventually, of course, quantum error correction as well. So all of these things are needed, and all of these things run incredibly well on NVIDIA's platform. And here's some stats there of some of the speedups we've seen, people already using our GPUs for algorithmic development for building better qubits for generating data and for quantum error correction. So all of these things, we provide value along the way, both today and into this eventual future. We believe that NVIDIA is a key part of that entire pathway, which is why we announced this week NVQLink as a way to connect, a standardized way to connect between QPUs and the supercomputing centers. And we can see we're working with essentially every major QPU builder. We're working with all of the major supercomputing centers. Jensen announced a deal with 7 national labs earlier this week, although I only see 6 on this slide, so one of them got inadvertently missed. And then the control system builders. So we're working with the entire industry to make this the standard for connecting from your supercomputer to your QPU, regardless of modality. And just to give you the broad slide here, whether you're a researcher, whether you're a hardware builder, the system integrator, a cloud that wishes to provide access to QPUs, we're working with everybody to bring this to bear. So I'm going to throw this back up here just to show you. I only got to touch on a few of these software products and these domains, but where CUDA is our core foundation, it's our platform that we build with the hardware and software in collaboration with each other. CUDA-X is that next step where we build these libraries and frameworks and models that enable our developers to build great things on top of that. And so if you have any questions, I want to thank you for coming at 5 o'clock on the end of the conference and welcome any questions.